So now that we've explained how to mathematically find what those coefficients are so that we can write our general wave function, which in this case we're going back to the one from 2 videos ago where there's a specific polynomial that defines this, we can write this as a superposition of an infinite number of our energy eigenstates. So let's use some symmetry arguments. We can actually use this to have some idea of what we expect, and then you would do the math to kind of verify that, but the symmetry really helps. So notice that if I look at that L equal, right, so this is x equals 0, this is x equals L, so around L over 2, it's symmetric. If I fold it over, I get the same thing. So if we come over here and look, this first one has the same sort of symmetry. The second one doesn't. When I fold it over, the left and the right side are opposites. That means this one is not going to contribute. There is no way to add this and get this symmetry. So this one would actually have a coefficient of 0. This one we look again, when I fold it left to right, it looks good. And then this one again has the same sort of symmetry as this one, where in fact it's opposite if we fold it over. So that one would not contribute. So what you see is that in fact only our m values, which are odd, are going to contribute, because the symmetry pattern continues up. So we've already found something, and so when you're starting down the math, it would be nice to mathematically verify this, but you kind of know if you get to a certain step that you need to split out the difference between your odd values and your even values, since some are 0. So the next thing to think about is to not make the mistake of saying, well, just flip this one upside down and that's it. That's not going to work, because notice that the 0 value here, like all of our values are positive, and in fact here, some of them are positive and some of them are negative. So one of the ways to think about doing this is to just say, well, okay, if I didn't want to do the math and I wanted to just trying to draw this out, how might it work? Well, so let's actually say, let's look at phi 1, and then remember, you can always do some overall phase. I could have drawn this in the opposite way. But let's actually subtract the third state from it, how I've drawn it. So basically imagine adding these together, but have this one be opposite, right? So briefly, I have this one, and then the next one, again, so another way to think about it is adding the opposite. So this one would go up. I always have to do it this way. So down, up, Okay, so those are my two functions. So now I can try to add them together. So it starts at 0 on the ends. I like that. It goes up, but then at a certain point, for instance, if I have these coefficients right, it could be 0 here. So it goes up, and then it actually has to come down to 0 somehow. That looks pretty good. Now, I'm not saying that if we add phi 1 and phi 3 together, we get this exactly. We are not going to. But you can see that it comes pretty close. So I would expect that when we add these together, we in fact get a pretty big coefficient for these two that might then decrease fairly rapidly, since it does look like these two do a pretty good job. So again, that's the starting point for thinking about this graphically. Please understand that this is the conceptual part here, is using symmetry arguments, thinking about it graphically, and use that as a check. That doing these integrals, which again is basically a Fourier transform, is going to be something that can be very challenging. You're now usually integrating a sinusoidal function multiplied by something else. You have to use those those integral tables in the back of the book, but to just check to make sure you're heading in the right direction, these sorts of arguments are really helpful. So I'll do a little bit more of this, focusing more on the math in the next video, but again, you can get pretty far by just conceptually trying to think through what's going on with this.